We are now getting to the paper before, entitled Conceptual Framework of a Digital Twin to Evaluate the Degradation Status of Complex Engineering Systems. It is written by our colleagues from Great Britain, from Cranfield, Exeter, and London. And the main author is David D'Amico, together with Jen Ekoyuncu, Sri Addepalli, Christopher Smith, Ed Keedwell, Jim Sibson, and Stephen Penver. We are excited to see the video.
Hello, my name is Davide D'Amico, and today I'm going to talk about my work titled Conceptual Framework of a Digital Twin to Evaluate the Degradation Status of Complex Engineering Systems, that I've done together with my research group based at Cranfield University, Exeter University, and Babcock International. Starting from an existing materials degradation assessment models, this work aims to integrate that model into a digital twin framework, which itself is capable of further integration into a wider digital twin architecture. The long-term vision might be to develop a digital twin for degradation assessment with the ability to predict the remaining useful life of the asset of interest. In scientific literature, as we can see from the graph, after the introduction in 2003 by Michael Greaves, the interest in digital twins grown fast. Initially, digital twins were adopted in the aerospace sector. Nowadays, the implementation of digital twin is increasing also in the industry sector. Most papers study digital twins for specific purposes, like monitoring specific conditions or planning and managing specific phases of the life cycle. The use of digital twins throughout the whole life cycle, instead, is still in its infancy. This is probably due to the huge amount of data that has to be managed and for the complexity of the integration of different models that have been created to work in a standalone mode. There are many degradation assessment tools existing today. They study a different kind of degradation that may occur in a product. A degradation model must be contained in a digital twin framework in order to estimate the remaining useful life of the system of interest. The integration of degradation assessment model in a digital twin has been already started. A few authors, indeed, implemented some aspect of the degradation evaluation in their work. However, this is a highly complicated task, but can bring a cost reduction throughout the life cycle and a more conscious decision-making process. Better monitoring of the health status bring about to predictive maintenance approach and, of course, to a better maintenance planning. We are in the context of complex engineering systems, or systems that last for a long time and need a plan for the maintenance. Also, for those systems, there is an increase in the employment of the modeling and simulation methods, and as a consequence, a growing amount of available data across the product life cycles. This led to the use of the digital twin paradigm, which can combine the two trends. Moreover, in these systems, the implementation of the degradation assessment tools will result in a more profound evaluation of the status. The proposed conceptual framework is shown in the slide. As we can see, we consider the digital twin as a group of modules connected. We have a central unit where every other module is connected to. Each module has its own block with its own software, which can be different from the other blocks. Then we have the interface in each block, which translates the data into the common language of the digital twin framework. Each module has also its own database, which can store the data that might be needed in future iterations. On the left side, we have the cloud module, which can store the learning algorithms that will feed the experience-based model. The latter indeed can be useful in the case of connection with other digital twins of similar assets. On the right side, the visualization module, in which different kinds of visualization tools can be used to show the output to the user, for example, browsers, virtual reality glasses, augmented reality glasses, or a combination of them. The conceptual framework is composed of three main layers: the data architecture, the models, and the integration, or better, interconnection across the modules. This is also the order in which the digital twin should be made. The way each module communicates with each other can be compared to the way the main data provider on the web shares the data with other websites, without allowing them entering into the provider's architecture. This occurs thanks to the Application Programming Interfaces, APIs. Here, for example, we can see a simple query response that may occur in the digital twin. The query is a structured string which asks to the system for a specific information, while the response is a JSON message that contains all the data that the query module might need. The central unit, thus, has the main feature of dispatching messages. It can receive a request from the module and forward them to the interested modules, ensuring the correct flow of data and messages. Furthermore, the central unit is also able to understand how many modules should be connected to the digital twin and checking their status, which can be on, off, or disconnected. This to ensure the maximum flexibility to digital twin. An example of model that can be adopted in a framework like that is a CAD model, which can provide to the system the physical attributes such as dimension, mass, inertia, center of gravity, etc. Another model can be the environmental model, which can provide to the system information about the surrounding area of the asset of interest. Most of the time, indeed, environmental condition is the only difference between two similar assets and can bring to a different set of issues. The learning module, as I said before, can lie into the cloud and can contain experience-based algorithms that enable the simulation of the what-if scenarios. And finally, for instance, the degradation model, which can use the geometry from the CAD model and the real-time status of the asset from sensor and 3D scanners to generate the desired output and provide useful information for the prediction of the remaining useful life. Concerning the Degradation Assessment module, we use the example of the Automated Tomography Inspection as a non-destructive test, NDT. When a part comes for service, the maintenance system performs the automated inspection using pulsed tomography. With the use of signal and image processing algorithms, thresholds are set up to identify critical areas showing degradation beyond acceptable levels. The degradation model for this feedback-based maintenance is dependent on the data from the inspection system, existing knowledge on the history of the inspected part, and on the remaining useful life algorithms that help predict and establish a time to failure with a confident band. We can simply integrate this model into the digital twin framework. We only have to split the part of the evaluation of the remaining useful life and put it into the cloud, where the learning algorithm. Moreover, Data-driven approaches, such as machine learning, used in a fleet context rather than a single asset, can help in a long-term production planning to reduce unpredicted downtime, thanks to a data log history contained in the fleet digital twin. Indeed, as I said before, if we consider the fleet instead of a single asset for this digital twin management, we can use the historical information from other digital twins of similar assets in the same fleet in order to use the experience in our asset of interest. In this way, the knowledge of my asset can be enhanced and, as a consequence, make improvements during the design phase. In conclusion, this work wants to provide the framework of an open architecture for a digital twin, which is what is currently missing in the scientific literature. We can find first examples of open architectures, such as Eclipse Ditto, which is an open source architecture, but it still has some limitations and compatibility problems. The digital twin can also be used to virtually test the asset in different environmental conditions, or to virtually perform maintenance, testing different parts. Moreover, it can also have the hardware in the loop feature, which allows us to test modules in a virtual environment. In this way, the digital twin becomes an essential tool that contributes for a more conscious decision-making process. Future work will focus on the application of this architecture to a real use case, benchmarking the different communication protocols and libraries to speed up and ensure the correct circulation of information across models. Compare the result of an integrated approach with the ones obtained by using all the models and simulators in a standalone way. The final objective is to reduce the effort needed for the models integration as well as the integration of different commercial and open tools. Thank you for your attention. I will be pleased to answer to your questions.
Thank you very much for the presentation of this paper. We're now trying to connect with Davide D'Amico in Cranfield. Hello to Cranfield, this is Francisco from Berlin, CIRPe. Can you hear us?
Yes, can you hear me?
Yeah, thank you. Thanks for joining us. Thanks for putting the presentation and the paper together. It is an interesting thing to see from the concept kind of way. Can you explain a little bit more what you mean with complex engineering systems there? So can you give examples? Can you explain that a little bit more?
Yes. Complex engineering systems are those systems that require maintenance and maintenance planning because they last for a long time. For example, engines, turbines, planes, ships. So are those systems that maintenance.
Can you repeat this, please? There was a technical problem on the way.
Yes.
So like the last two sentences.
Complex engineering systems are those systems that last for a long time. So they require a maintenance plan.
Okay. Thank you very much. So as we understood, there is a world of methods apart, and your paper is trying to propose a framework that integrates these parts. I wonder about, there is a lot of effort that is needed to do this kind of integrated approach in there. In what sense is the reward of that kind of integration to be expected?
Yes. basically, nowadays the approach is to problem with silos, with standalone approach model, and then we use the data from our model to do another model and so forth. The idea of this approach is to have everything in one framework, in one structure, and let the models communicate each other in the way that they can share the data they need real time, and we can have the information we need real time, and so we can help our system to predict some failure to avoid downtime of the machine.
Okay. Does that mean more complexity, or does that reduce the complexity?
This means a lot more complexity, but more.
That was not clearly transmitted to you. Can you repeat that, please?
Yeah, it means more complexity, but also more flexibility.
Okay. What would need to be done in order to evaluate whether that is worth doing?
We need to develop the framework. We need to establish the common language of the digital twin, because each module connected to the digital twin should speak the same language. Mm-hmm. So the main part is to build the interface that can allow the models to speak with the digital twin. So mm-hmm. I think the main part is to let the model speak the same language.
Okay, so we're keen to see your future research in order to get that up and running in Cranfield. So thank you very much for joining us in that question and answer session right here. Davide D'Amico, thank you very much. Goodbye.
Yeah, thank you. Thank you so much. Bye.
So this was the paper presentation and the question and answer session of the paper, A Conceptual Framework of a Digital Twin to Evaluate the Degradation Status of Complex Engineering Systems by the colleagues from Cranfield, Exeter and London, Davide D'Amico, John Ekoyuncu, Sri Addepalli, Christopher Smith, at Keedwell, Jim Sibson and Stephen Penver. Thank you very much.